talk is Xiongfeng Ma from Tsinghua University. Take it away. You have 35 minutes.
Okay. All right. Thank you. Yeah. This is Xiongfeng Ma. Yeah. I'm sorry I cannot be come to Toronto due to the visa issue. Today I'd like to talk about a little bit about the NISQ devices. What kind of limitations we have for the computation and also the entanglement. This is a joint work with my students. Let me just work out the point. Yuxuan, Zhenyu, and Junjie. So this is the outline of the talk. First, I will give a brief introduction about the NISQ device, and then I will move on to the what kind of limitations we have for computing. Then I will talk a little bit about the limitations on entangling power as well. Finally, I will give a outlook and conclusion. Introduction. So I'm not sure if someone else have shown this picture, this image in the workshop. So today we have lots of investments in the quantum technology, especially quantum computing. So here, this is by the last year. So some people even say that we put too much investment in the quantum technology. The question is what kind of outcomes we have. Okay, so we have invested lots of resources in the quantum technology. Okay, what kind of outcomes we have? Definitely, we have quite a bit of the solid outcomes. For example, we have shown that with quantum devices for some specific problems, we can solve them. We can solve them faster than classical computers, especially for those with the quantum sampling problems. In different kind of systems, like superconducting system and also linear optics as well. We also have theory shows that even with shallow circuits, we might provide some advantage. And then today, what do we have for the quantum computing device is today we call the NISQ area. We're talking about the hundreds of qubits, maybe 1,000 qubits. And then we have to deal with the errors and the coherence. We cannot really correct the errors. So we are not the fault tolerant yet. And at this moment, we have finished the quantum advantage demonstration. So we can solve some specific problems faster than classical computers, as we just mentioned in the previous slide. The key question that the main problem for those advantage experiments is that they are not practical or useful in practical sense. So at the moment, our current focus is that can we find any practical and useful problems that we can show that the quantum devices can outperform classical devices. So we want to check out what kind of boundaries we have for the NISQ devices. Okay, so there are definitely a lot of very exciting developments going on in the past few years. For example, last year, IBM's Ising experiment. Okay, so there were like 127 qubits. It's noisy qubits, and then they demonstrate this Ising model. Unfortunately, only a few months later, there were a few groups. Here I only list two. There are a few groups. They show that for this experiment, for this particular experiment, actually, if we use more advanced, more efficient tensor network simulation method, you can use a classical computer to simulate these devices. Those experiments are very efficiently. So those experiments are very good, but they are not. We cannot show quantum advantage with these experiments. Okay, now one very interesting question is that where are we? Okay, so if in the next few years, if we want to show really in one practical, useful question, if we really want to show that we can get some quantum advantage, and then we want to check out the boundaries. Okay, we know that in the far future, if we have lots of qubits, okay, the x-axis is the number of qubits. If we have lots of qubits, like millions and billions of qubits, And then also we can keep the error rate very, very low. Let's say gate error rate is very, very low. Let's say below to like 0.1% or even 10 to the minus 4. Then we can use those nice error correction code to reach this fault tolerant quantum computing. So they are very useful. We already know that like in the 90s, like for example, the Shaw's algorithm, Grover's algorithm, HHL algorithm, etc. And then when number of qubits is very, very small, let's say if we only have like 50 qubits, even 40 qubits, then it's classically simulable. We can use a classical computer to simulate a small scale quantum computer. Okay. So and also if even if the number of qubits is big, but if the error rate is too big, then we can still simulate it because it becomes very noisy. It behaves like a very kind of white noise. In between is we call the NISQ area. NISQ area. This is somewhere what do we have nowadays? The quantum devices. What do we have? Okay. The question is that okay, what's this line? What's this line? Where this line? What's this boundary? This upper bound. Okay. All right. So here we want to find some. So the ultimate goal is we want to find some questions here that we can demonstrate quantum advantage. So first question we want to ask, okay, where is this boundary? Okay. So this is the main motivation for this talk. Okay. Before we go into the this upper bound or this limitation, we need to know that it's not really only about the NISQ device, the computing power of the NISQ device. It's also we can also combine the classical post-processing with the NISQ device. Okay. For example, what we can have is like okay, we can have some interface with the NISQ device, NISQ quantum computing devices, and also we have a classical computer to assist this computing. For example, we can put the kind of the hard parts to the quantum computing device, and the easier kind of a classical easier question for the classical computers, then we put back to the kind of classical computer. So this is a kind of hybrid of the quantum and the classical computing devices. Okay, so this is very useful in the past few years, especially we have like different kind of proposals like variational quantum methods and also error mitigation examples. For example, if we use those variational method, we can lately we have some proposals showing that okay, we can solve some of the quantum chemistry and the material problems. We can simulate some of the small molecules with quantum computing devices, with near-term NISQ devices. And also we can use some other technologies like error mitigation, and then we can enhance the fidelity of the quantum computations on the NISQ devices. But in both this VQE and also error mitigation, we both have this scalability problem. In the past few years, we found that okay. So for those kind of hybrid method, we still have the scalability problems. If we have more qubits and deeper circuit, then we have so this classical computing, this part becomes heavier and heavier. Eventually, it will go to exponential. So eventually, it's not efficient. It seems like there's a kind of, for example, in error mitigation, it seems like we have a trade-off between the mitigation overhead and also the computation accuracy. So if we require very accurate, precise results, then the mitigation overhead becomes very, very big. Okay. So then we can see that we have seen these kind of limitations in the case by case. We generally believe that for many methods, we do have this kind of limitation in the computing. So now, in order to figure out what kind of upper bound, what kind of computation limitation in for the noisy quantum devices, we have to have some assumptions. Because if we don't put the assumption correct, then we might have inherently we might have fault tolerant computing devices. If the error is low enough, and if you allow to perform some measurements and do some feedback, essentially you can perform error correction. Okay. So here are the assumptions. So first initialization, so we initialize the state to be all the qubits into the 0. Okay, so this is a very reasonable assumption. So this one we are trying to avoid that in the very beginning somehow magically we have one quantum state somehow can pop up naturally, and then by measuring that quantum state, you can already solve some let's say some very complicated classical problem. So we try to avoid that, which is also possible in principle. So that's the first one. Second one is the local connectivity. Okay, so we assume that it's the qubits applied to the system it's local. Local means that you can only apply the handful of the qubits. Let's say 2 qubits, 3 qubits. You cannot just directly apply n qubits quantum gate. Otherwise, we cannot really count number of gates. We cannot really specify the circuit depth. Third assumption, the first two assumptions are quite reasonable. So basically, pretty much apply to all the quantum systems. The third one is a very specific assumption. So we assume that the quantum device suffers from the independent single qubit deployment noisy channel. So that means that after each layer of the quantum circuit, each layer of the gate, each qubit has some probability. This probability we denote by p. There's a probability p. This qubit will lose all the information. Just becomes a white noise. Okay, you cannot really recover it. And then with 1 minus p, it will stay free. Our recent results show that we can relax this assumption a little bit, but I will talk about it in the end. The fourth assumption is that we do not allow any middle circuit measurement and the refreshing operations, because if we allow general middle circuit measurements and the refreshing operations, then we can do error correction. Okay. So this is again, it's a little bit strong assumption, because in general in the lab in the experiment we can really perform some in the middle. We can perform some measurement, and then we can introduce some new qubits. Okay. So, so this one is kind of a strong assumption for this work. So that means that implies that once information is disturbed, we cannot really retrieve it. Finally, the computation-based measurement is similar to the first one. Okay, so this is again, it's a very typical assumption in the quantum computing devices. Okay, now we want to combine this hybrid system. Like one is the quantum device, and also the other one is a classical device. Okay, so here we put the model here. So this model is that so we do this iteration. Okay, so first classical computer will run some computation on the input X, classical input, and then send some information to the quantum computing device, and then run some circuits, and then perform some measurements, and then feed this measurement back to the classical computer, and then go back forth. And then sometimes the circuit depth is very deep. Sometimes it's very shallow. Okay, here we use color. So when the color is so for this kind of faint color, we want to show that this circuit is very shallow. When this is the color is when the color is deeper, that means that the circuit is deeper. Okay, so if we look at each block of this disk device for this disk device circuit, is that you look at this one. Initially, you have all 0. Finally, we have computational-based measurements. In between, it's the layers by layers of the circuit. Okay, again, each circuit, each layer of the gate is local. It's localized. And then here we assume that after each layer of the gate, we have a departing channel for each qubit. They are independent. Here we have to consider the total running time, okay, including this classical computation, okay, and also because otherwise, with if you allow this classical the assisted classical computer to run exponentially long time, then you can just let it do all the job. Okay. So we have to counter all the running time. Okay, here's the main result. Okay, so the first main result is that if the depth, so again, come back to this picture. It's like for this different NISC devices, the depth of these NISC devices is different. The circuit depth is different. Okay, So if the circuit depth is if it's go beyond, so t is time, is the refer to the circuit depth. If the circuit depth is go beyond the log of t, okay, t we get tm. We can think of the this is the efficiency of the algorithm. So for the moment, let's just assume that this is the polynomial of the log n. Okay. So typically tm is the polynomial of n, because we only consider the one algorithm that is polynomial in n. So then this log tm will be in the order of log n. So eventually here it says that okay, when the depth of the circuit is go beyond the log of n, okay, log of n, then it could not. Then this kind of circuit cannot provide any quantitative advantage. Okay. Again, let me keep in mind that this running time Tn should be added all the time together, like a classical computing time, quantum device time, and also the single qubit matching as well. Okay, so including all the time. So if this Tm is let's say polynomial in n, okay, which is something what we are interested in, then this kind of it's too deep. Okay, if t is larger than log n, it's too deep. So it behaves like a random coin. So there's we cannot really distinguish this random coin or this very deep quantum circuit. So here I want to, if you have any questions, feel free to interrupt and ask. Otherwise, I will just continue. Okay, so let me just give you some examples. Then I will show you some what's the implication for this theorem. It says that okay, if we use this kind of given those assumptions, given this theorem, it says that okay, with this NISQ algorithms, then we cannot really have any exponential kind of exponential speed up for lots of well-known algorithms like the Xiongfeng algorithm, global algorithm, extraterritorial algorithm, for those algorithms. So here is basically say that if you don't do error correction, if you I shouldn't say that, it's like if you assume those 5 assumptions, roughly speaking, it's like NISQ devices, we cannot really factorize big numbers. Okay, we cannot really do this global algorithm to search for kind of optimal result, etc. So this also again is implied in a lot of earlier works. So again, so those kind of case studies. But in this work, we really put it there in kind of very general results. Okay, so the main proof technique comes from this Aronoff, and so the first result is shown in the Aronoff's paper, and also later on the result is shown more rigorously in Muller, Hemmes, and his colleagues' paper. Okay, let me just quickly show you what's the results. Okay, so this result shows that okay, if we have this kind of deployment channel noise, okay, so basically like after each layer, each qubit will have probability p to lose all the information, and then you don't really retrieve this information with error correction. Then slowly, this whole system becomes more and more close to the maximum mixed state. And then they show that this very strong results show that okay, the distance measured by the relative entropy, the distance between the final state and the maximum mixed state. So basically, maximum mixed state is just 2 to the m to the I divided by the 2 to the n. So this is the maximum mixed state. This is just a random coin. If you measure in the computational basis, this is just a random coin. Okay, so the distance between these two states is exponentially small with 1 minus p. So again, p is some constant. And then when t increases, when the number of layers increases, this distance, the state becomes very, very close to this maximum mixed state, this use-case state. So this is the main technique we use to prove this our main result. And so what do we use? And then so what do we use is the entropy analysis. Okay, so eventually what we show is that okay, even with this kind of interaction between the classical computer and the quantum computing device, for each this kind of box, if the steps is if the circuit depth is go beyond the log of n, then this whole box we can later on we can just replace by the classical random coin. So that's a picture. So if it's too deep, then you can just replace it with a random coin. Okay, and then if it's very shallow, then if how shallow? If the circuit is below log of m, we know that the classical computer we can use a classical computer with the polynomial of m to simulate a log of m depth of the classical quantum computer. So here that's why we show that okay, there's no exponential quantum advantage with this kind of devices. So here we only show that okay, if the circuit depth is beyond the log of m, then it's behave like a random coin. So if now we limit our results that okay, it's the one-dimensional system, like a Ising chain, looks like an Ising chain. And then if it's a one-dimensional, then it's so this results can be extended to even for the case that the depth is less than. Here, so we use the results, the very nice results by the Ravi and his colleagues. They show the reverse smart kind of light cone. They use the principle of the light cone to simulate this one-dimensional system. So they show that if it's a one-dimensional system, then if the circuit depth is t, if the circuit depth is in the order of log of n, then you can simulate it with the polynomial of n with a classical computer. The main idea is that okay, you don't really need to simulate all the qubits at once. All you need to do is like a simulation. So you want to figure out one qubit's measurement results first, and then because of the depth is very, very shallow, only a few qubits will affect this measurement results. So this is kind of a light cone argument, and then you go one by one. Repeat this procedure. I will skip this one due to time limit. And then we show that okay, with this one, we show that okay, for one-dimensional system, it's we cannot have any kind of super polynomial advantage. Next, I'd like to talk a little bit about entanglement. So we know that in the quantum computing, we know that there's a very strong link between the entanglement and also the entanglement and the quantum computing. Although we know we do have common examples showing that okay, even with a very, very little entanglement, we can show some quantum advantage. But in general, we know that we do need entanglement to show. Excuse me. We do need entanglement to show most of the kind of quantum algorithms, especially like if we want to go to the quantum error correction, we know that there are lots of entanglements. So here we want to show that if you for this kind of NISQ devices, we have a very limited power on this computing. Here, I also want to show that similarly, because of this kind of fundamental link, we also have limitation on entanglement power of the NISQ devices. Okay, this is a third theorem. So again, for entanglement case, we show it with the restriction of the topological connection with the qubits. Okay, the first result is that if the system is the one-dimensional, again the link is like one-dimensional. Then again, so all the gates is local. Local means that all the gates you can apply you can only apply a few qubits. Okay? Then in this case, no matter how you apply the circuit, so if you separate eventually, okay, no matter how big it is, this lattice, one-dimensional lattice you have, and then as long as you apply this kind of noisy gate, and then if you separate the whole circuit into two parts, or you can take any two parts, then the entanglement, no matter what kind of measure you have, you can, because we use the mutual kind of a mutual information, and then the entanglement between these two parts is less than, it's bounded by log n. Here we have a very strong kind of intuition. We want to show that the actual is not log n. but we couldn't show it. We want to show that it's constant. I think that's our conjecture is that this number should be constant. So basically, with noisy gate, for one-dimensional system, you can only have a constant amount of the entanglement. And for the two-dimensional case, the result is a little bit loose. So we can prove it's less than square root of n times log of n. Again, with two-dimensional system, it becomes we can see that it becomes much more powerful from the entanglement point of view. So this will give us a lot of local examples in the simulation. Okay, so again, the proof is we basically use a Lycombe argument. So I will skip there due to time limits. Okay, so here there are a few open questions here I have. So the first one is like, how can we, because those upper bound, how can we go beyond those upper bound? Then there are a few things we can check the assumptions. First is the depolarizing channel. So in lots of channels, they are not depolarizing. So mainly it's caused by, let's say, dephasing. If it's dephasing channel, can we do better? And also, what if we allow a limited amount of the error correction? So it's not necessary. It's basically like in the real experiment. It's not necessary that we just run the system and then perform the measurement. We can do a little bit experiment, but not fault tolerant yet. And then can we do better? Can we find the much stronger result? And also we want to try to tighten the upper bound on the entanglement generation. And then so basically this picture will give us like where to look. Okay, so if the depth is beyond the log of n, then it's too noisy. So the whole circuit looks like just a random coin. If it's below log n, then for one-dimensional system, it's useless. But if for two-dimensional system or like an arbitrary connection, then there's still chance to find some advantage for the quantum computing. Okay, so basically like if for the near term, if anyone want to find some practical problems to be useful and also to be practical, this is the place. This is red block. This is the place we can find. Okay, so at least it's two-dimensional kind of two-dimensional connection, and also the depth is below log of n. Of course, we also have this parameter p here. In the experiment, if we have a very small p, we can still work it out. Of course, the other argument is that it's p very small, then we can just directly shoot for the error correction. Anyway, so this is the kind of the outlook. Oh yeah, I'm sorry. I go back, and then that's all. Thank you. Any questions?